Everyone. All right, this is for section 5.4. The title of this section is The Fundamental Theorem of Calculus. If that doesn't sound important to you, then you're just not paying attention. And the word fundamental there tells you something. Um, it's a big deal, okay? And if you think in terms of the AP exam, on the AP exam, they gear a lot of questions towards the fundamental theorem of calculus. Now, we actually have some familiarity with this, and you'll see that in a moment. Something we've already learned under a different name will be renamed as part of the fundamental theorem of calculus. But just to put this into some historical context a little bit, you know, prior to Isaac Newton and Leibniz, Gottfried Wilhelm von Leibniz, in their work, there were these seemingly unrelated set of tools or loosely related set of tools in mathematics dealing with rates of change and area bounded by curved objects. And most of these things were approached as parts, separate topics. One of the great insights between or made by Leibniz and Newton was this connection between these two seemingly different parts of mathematics. And it's this idea that comes up in the fundamental theorem of calculus. So it's a big deal, and it was sort of the unifying concept between these two things that out of which came this whole subject of calculus. Just some other little historical notes. There's a fundamental theorem of arithmetic that you probably don't remember from an earlier class, and it has to do with the factorization of the positive integers. And it says that the positive integers have a unique prime factorization. And so that probably sounds familiar now that they mentioned it that way, but under the title Fundamental Theorem of Arithmetic probably doesn't ring a bell. There's also a fundamental theorem of algebra, which talks about the number of solutions or number of roots to a polynomial of degree n. And the polynomial of degree n has n roots, is a simplistic way of saying it. But nonetheless, there are fundamental theorems from other mathematical topics, and those two are ones that you've seen, maybe not by that name, but you've seen them before. All right, so what is the fundamental theorem of calculus? Let me at least point out one more time that seeing this word here, this means that this is important. Now, there are some mathematicians that will tell you that maybe there should be a different theorem that is as the fundamental theorem. Like maybe the mean value theorem is more of the fundamental theorem of calculus than this theorem here. But and they have arguments that could support that. But as far as we're concerned, here's our fundamental theorem. Let me reveal it to you. And again, you've seen part of this already. So the fundamental theorem of calculus, let f be continuous on the closed interval AB, then there's two parts to it. The second part, which I'll address first, is the evaluation theorem. This is something we learned in the previous section, and it shows that if we want to evaluate a definite integral on the closed interval AB, and again, this is provided that the function is continuous on that closed interval AB, then we just need to find any antiderivative of lowercase f. That's what this part here signifies. This is any antiderivative of lowercase f. And from there, we can just plug in b into that antiderivative, plug in a, and then subtract, and that'll give us the value. The part that we haven't learned is this part that's number one. And what this is saying, without saying the symbols here, it's essentially telling us that taking an antiderivative and taking a derivative are inverse operations of each other. If you think back to inverse operations like addition and subtraction are inverse operations, and multiplication and division are inverse operations. Inverse operations undo each other. And that's what this part is telling us here. If we take the derivative with respect to x of this integral, which is an integral from a to x of f of t dt, then essentially the derivative and the integral are going to cancel each other out, and we're left with just f as our answer over here. Now notice it's no longer f of t, it's f of x, but still the derivative and the integral have canceled out. So um, this is the big idea that when dealing with rates of change, which is what the derivative was dealing with, measuring how fast things are changing, and integrals. Graphically, we're giving us an area bounded by a curve or a net signed area, or another way of putting it, how fast things are accumulating, which is something we talked about a little bit in 5.3. Maybe not with those words, but an integral of a rate told us a net change in, net change in distance, net change in volume, net change in something. So we were looking at the integral as an accumulator in that one, how fast things were piling up based on the rate. And this is saying that if I take the derivative of that integral, those things are going to cancel, and I'm left with that function. But it's a function of x, because in this expression here, t is a dummy variable. T just is essentially a placeholder for the expression that we write in the integrand. When we write the integral from a to x is our variable. Okay, x is what this is a function of. And then we're taking the derivative with respect to x. And so our answer has to be in terms of x, or in terms of that input variable. Now, the fundamental theorem appears quite frequently and profoundly all over the AP exam. So it's something that we want to make sure that we're familiar with, that we can perform the necessary parts of this theorem that's required of us, and apply it to different situations. And we'll look at some of those different situations in which we'll be able to apply it. So don't panic, but just know that, even the title tells you, take this with some seriousness, that you need to know this and you need to understand how to apply it in different contexts. And I'll show you those different contexts in which we need to apply it. Obviously, part two, it's also known as the evaluation theorem. You're going to be using that a lot to evaluate definite integrals, but we'll be using number one a lot for various things as well. And so we'll take a look at that in just a moment. Apologize for any background noise. I am recording this outside, so if you hear any background noise, again, hopefully it doesn't drown me out. So let's evaluate the following. So just as a side note, in many of our examples here, we're going to be focusing on part one of the fundamental theorem, because we've already practiced part two quite a bit in the previous section. But some of those examples will be mixed in anyway. So we're taking the derivative of some integrals. So we're focusing on part one. And so there it is. And here are a couple of examples. What I would love for you to do is to pause the video and see what you get for these answers, for the answers to these questions on your own, and then compare to what I get, and then you can make adjustments. You can see how well you understand it from the beginning, and how much help you need to get from me after the fact. So pause the video, please. All right, so hopefully you have an answer with which to compare to mine. Right or wrong, something is better than nothing. So now, what I said earlier was that essentially, as long as the function's continuous on the given interval, the derivative and the integral are inverses of each other. They're going to cancel each other out, okay? So this example here, and they will get harder, but this example here is as easy as this. The answer is just going to be the square root of 1 plus 2x. That's it. The structure of this problem is exactly the same structure as what we have up here in the fundamental theorem. Okay, exactly the same structure. And the derivative and the integral here cancel each other out, leaving just the integrand. I don't like those circles right there. They're kind of in the way. But nonetheless, and leaving just f. See, f is right here, f is right there, f is right here. Okay, and that's essentially what's happening here. So they look exactly the same. So I'm just going to cancel the integral out, and I'm going to replace t here with the x that's here. And so we end up with the square root of 1 plus 2x, and that's it. All right, for part B, pause it now. If you didn't try part B yet, go do part B. It should be very simple for you right now. Pause it and go get the answer without me having to show you. All right, so Again, the derivative and the integral are going to cancel, and this is just going to be the natural log of x. Now, these two examples are really simple, and they are going to get a little bit more complicated, but not terribly so. But this is easy. This is a real easy application of the fundamental theorem, and you'll see how this is going to come into play in some examples similar to what's on the AP after a little while. Let's try these two examples here. Okay. Again, please pause the video, write out what you think the answers are, and then check your work against mine. All right, so if you notice the structure that we have in our integral here, it's not quite the same structure as what we had up here in the theorem, okay? What's different? Well, notice our variable, remember, x is our variable in the upper limit of integration. A is, it's a letter, but it's not a variable. A is a constant, okay? We know A, it's the endpoint of our interval here. So A is not a variable, it's just a parameter, if you will, a constant. X is our variable, and to apply the fundamental theorem, we need x as our upper limit of integration, or our variable as the upper limit of integration. But down here, x is the lower limit of integration. So I can't apply the theorem yet because it doesn't have the right. This expression doesn't have the right structure. So I need to rewrite it first in order to have it have the right structure to apply the fundamental theorem. So I need to get the x from being in the lower limit of integration to being in the upper limit of integration. Hopefully you remember this. I gave this to you as a property in section 5.2. And so you can go back and reference notes there to figure out exactly what I'm getting at here. But we're going to rewrite this first into an equivalent form. So I'm not taking the derivative yet. I'm not going to evaluate the integral. In fact, you won't be able to properly evaluate this integral. So what I'm going to do is I'm going to rewrite this as the integral from 0 to x of sine squared t dt. Now, hopefully you have a red flag going up. Wait, how do you do that? You made a mistake. Well, it's incomplete yet because I know what I need to do, and I just haven't done it because I'm hoping you think of it first. When we switch the upper and lower limits of integration, the result is opposite of where they were originally. So now, instead of this being the definite integral from x to 0 sine squared t dt, now this is the opposite of the definite integral from 0 to x of sine squared t dt. Now that the upper limit of integration is is now my variable, my lower limit of integration is a constant. Now I can work this out, and we have the negative here is just going to mean that our result is the opposite of what the derivative of the integral is, or we're using the constant multiple rule, so this is going to be the opposite. That negative is going to come down, and now I'm going to use the integrand here and just replace t with x, and this is going to become sine squared x. And that's it. Go ahead and give D a try if you haven't done it yet. So we need to do the same thing here in part D. We need to first rewrite this so that it's the opposite of the definite integral from 10 to y of tangent theta d theta. And then now, wait a second here. I rewrote that wrong. That should be a d over dy, not a d over dx. Excuse my little typo there, not paying close enough attention. Now this is going to be the opposite of the tangent of y. Now, don't put tangent of theta because theta is a dummy variable here. Okay, so your answer has to be tangent of y because our variable here is y and we're differentiating with respect to y. The answer needs to be an expression in terms of y. All right, here are a couple of more examples to try. So go ahead and give them a try and then come back and see how well you did. So in letter E, we have to do what we've been doing. And so we'll rewrite the order of the limits of integration, flipping them, making the result or the integral opposite. And after that, it's just a simple matter of making this negative I'm replacing t with u, so I get u squared sine u, and that's it. The opposite of u squared sine u. That's the answer. It's that simple so far. If you haven't tried letter F yet, letter F throws a new wrinkle on things. So give it a try. Don't be afraid to break it because you're not hurting anything right now. You're just trying to figure out how things work. And if you do it wrong, we'll fix it. And if you do it right, then you know you're understanding this at a high level at the moment. All right. The difference with this one from the previous one is we don't just have an x in our upper limit of integration. We have a 1 over x. And so to work this one, there's nothing to flip here. My variable is in the correct place. 1 over x is in the upper limit of integration. I need that so I can technically apply the fundamental theorem. But there's something else we have to apply, and hopefully you thought of this and noticed this. And if you didn't, that's okay. Most people don't. I don't think I would have at your age. No, I know I wouldn't at your age. So if you did, great. And if you didn't, well, then we're all in the same boat. What I want to bring up here is just a little recollection. I'm going to offer you an expression that'll help you hopefully think about what we need to do. Because this is essentially what we're doing here. Now, hopefully this is triggering for you the chain rule, okay? This is what we need to do here. We're going to have to apply the chain rule. The 1 over x that's in our upper limit of integration here is a function, okay? So we have an inner function, 1 over x, just like g in our little notation down here. And our outer function, the f, if you will, is the integral in terms of x, the integral from 2 to 1 over x, our tangent. So we have to apply the chain rule. Now remember, to apply the chain rule, this is going to be f prime of g of x times g prime of x. Whoops, like that. There we go. And that's what we're going to do when we take the derivative of this expression here, okay? So what does the answer become? All right, well, we'll do this in steps. Okay, so taking the derivative of the outer function first, f prime, leaving the inner function alone. The outer function is our integral, so I need the derivative of the integral. Those are going to cancel. And I'm going to get that arctangent function evaluated at the inner function. This is where the g of x comes. So normally I would put an x here, but now I'm going to put the inner function 1 over x. And then the next thing I need to do is to multiply by the derivative of the inner function. So I need to multiply by the derivative, with respect to x, of course, of 1 over x. So I have to evaluate that. So I'm not done, but that's what I need to do. Okay, so this becomes arctangent of 1 over x times negative 1 over x squared. That's the derivative of 1 over x. And so keep in mind, the chain rule applies, when we come into a function composition situation, which is what we had here. All right, we'll try some more examples. All right, so here are 2 more examples that I would like you to try prior to watching my solution. Pause the video, go give them a shot, and see what you come up with. All right, so same situation as we had there in letter F. So our upper limit of integration is our variable. That's good. Lower is constant. It's also good. And we're just going to have to apply the chain rule to this. So the derivative of the outer function, so the derivative and the integral will cancel. We will replace these 2 t's here with our root x. And so we're going to end up with cosine of the square root of x divided by the square root of x. And now we have to multiply by the derivative of root x. And I'm not going to write it out like I did in F. I'm just going to go into taking the derivative of root x. The derivative of root x is 1 over 2 root x. And if you don't remember that or how to do that, you should go work it out on your own off to the side. But you can rewrite x as with a fractional exponent, x to the power of 1/2, and then apply the power rule, 1/2 x to the negative 1/2. But x to the negative 1/2 means the term is in the denominator, so it's just 1 over 2 x to the 1/2, or 1 over 2 root x. Just as a side note, on the AP exam or on a multiple choice test, you're probably not going to have the answer listed this way. I mean, it could be, but they would probably multiply together. And so 1 times cosine root x is just cosine root x, and 2 root x times root x times root x is just x. So this would be 2x here. And so that's probably how the answer is going to be listed on a multiple choice test. All right. If you haven't tried H yet, please go give it a shot, but I'm about to, so there I go. Same thing, the lower limit of integration is constant, the upper is variable, that's what I need, and so the upper limit is a function, so we'll apply the chain rule, and so the integral and the derivative will cancel, leaving 1 plus, r is going to be replaced with x squared, so x squared cubed. You could just write x to the 6th, but I'm just trying to be a little bit more careful and deliberate. And then all of that times the derivative of the inner function, and the derivative of the inner function, of course, derivative of x squared is 2x. So you might write this as 2x times the square root of 1 plus x to the 6th. There's the answer. Okay, so let's take it to the next level and look at these two examples, letters I and J. Now, if you go back to the fundamental theorem, you're going to notice that these integrals don't match the pattern that's in the fundamental theorem. In the fundamental theorem, we need the lower limit of integration to be constant and the upper to be variable. And here, both are variable. So this doesn't match the pattern. How do I apply the fundamental theorem to this? Okay. Well, like I said, this is the next level, and you may be able to come up with an idea using a property that we went over in section 5.2. I'd love for you to try to figure that out on your own. So now's a great time to pause the video and try. Don't worry about breaking anything, because you're not building a bridge with this knowledge right now. You're just trying to figure out how it works. And if you make a mistake, it's easily fixed. So don't worry about doing it wrong. Just do it, do something, and then come back. And if you got it right, great. You really have good insight right now. And if you don't, then you can figure out how to adjust your insight, and you'll be better off for it. All right, but I'm going to give it a shot right now. So again, I need my upper and lower limits of integration to be in a certain pattern, and I don't have that here. So I need to get a constant in one of my upper and lower limits of integration. Now, one of the properties that we went over in section 5.2 dealt with a way of breaking up an integral into two separate integrals. So I'm going to break this integral up into around a constant, 2x and 0. Okay, so I'm going to go from 2x to 0 of this u squared minus 1 over u squared plus 1 with respect to u, and then add to that the integral from 0 to 3x u squared minus 1 over u squared plus 1 with respect to u. Now again, we had a property about this in section 5.2. So if you didn't find it, now you can go look it up. The 0 doesn't really matter if the 0 is in between 2x and 3x. All it matters is we use some constant, and 0 is the easiest constant to use. Now the second integral we have here, this is the correct pattern. We needed the lower limit to be a constant. We needed the upper limit to be variable. It is. Over here, we're back to the case where the variables in the lower limit and our constants in the upper limit. But we learned how to handle that, so we should be able to deal with that on our own from previous examples. This would, take the opposite, flip the upper and lower limits of integration. Whoops, no du down here. Excuse my miswrites. U squared plus 1 du. And now in this form here, we can go ahead and apply this fundamental theorem. Okay, so I get negative, or the opposite of this fraction, not u anymore. I'm going to replace the u with 2x. So I'm going to get 2x quantity squared minus 1. And you don't have to write it like this. You can already expand it a bit. So it's the opposite of this, and then I have to multiply by 2 using the chain rule because the derivative of 2x is 2. And so now I'm going to get 3x quantity squared minus 1 over 3x quantity squared plus 1 times 3. I'm going to forego any simplifying, but that's an equivalent answer. If you want to simplify, go right ahead. I just don't want to take that time right now in this video. All right. Go ahead and try that. Apply that principle here to J. Pause the video and go see if you can get the right answer. All right. So hopefully you did, and you're just confirming it against my work here. So we'll go negative 5x to 0 cosine u squared du plus integral from 0 to 5x cosine u squared du. And then the first one, again, has the wrong order in the limits of integration, so we will flip those. And we're going to get the opposite of the integral from 0 to negative 5x cosine u squared du. The second one has it in the correct order, so there's nothing to change there. I think I put a dx up here because I'm going too fast and not paying attention. All right, now let's go and apply the fundamental theorem. So we get the opposite of the cosine of negative 5x squared, and then we have to multiply all that times the derivative of negative 5x, which is just negative 5, plus cosine of 5x quantity squared like this. And then again, we have to multiply by the derivative of that inner function 5x, which is 5. So if we're to work this, let's do a little bit of algebra here because this one seems to simplify nicely. Negative 5 times a negative just makes it 5 cosine of 25x squared plus 5 cosine 25x squared. So this would work out to be 10 times the cosine of 25x squared. All right. You don't see too many of the examples like in letters I and J on the AP exam, but just in case, I want you to be able to see those. I'm going to give you a more typical example of things that we see on the AP exam. So I'll set that up and be back in a moment. All right, we're going to call this example number 2, but it's coming out of your textbook, section 5.4, number 3, at least in an old version of the textbook, unless they've, in the updated version that you guys have, I guess it could be different. But it says let g of x be equal to the definite integral from 0 to x of f of t dt, where f is a function whose graph is shown. And then it wants us to evaluate these values, g of 0, g of 1, 2, 3, and 6, and then figure out where, on what interval g is increasing, where does g have a maximum value, and then we want to get sketch a rough graph of g. All right, so let's try to work out the details of this. Now, the key thing here is utilizing the fundamental theorem, okay? As I've said a dozen times already, it'd be great if you pause the video and go try to work this out on your own a little bit and then see what you come up with. But I'm going to continue. So fundamental theorems are going to come up here in several different ways. For instance, g of 0, what is that? That's the definite integral from 0 to 0 of f of t dt. Well, what's that? Again, referring back to section 5.2 and the property that we had, we saw that when we have the same upper and lower limits of integration, that the value of the integral is 0. So that one uses just a property that we found earlier. What about g of 1? Well, g of 1 is going to be the definite integral from 0 to 1 of f of t dt, and we just got to think about how we interpret that. If you remember graphically, the integral either represents area or net signed area, depending on whether or not you are, whether or not the function is positive or negative. So if I go back to the graph over here from 0 to 1, we're just talking about this value right here, the area under the curve. I didn't shade it in completely, but I guess I could do a little bit better job here, like this. I need that area. Well, that area is just, it's 2 squares, if you can see it. So just 2 units, or, it's a rectangle, base times height, 1 times 2. And so that one's 2. I'm going to erase that now, if I can. All right. And then you need G of 2. If you didn't see these things before, didn't make these connections before, that's fine. Pause the video now and go finish working these out without me. Anyways, the integral from 0 to 2, so that's going to be the area, of all of this stuff in here. You can just break it down. So actually, let's get rid of that. From 0 to 2, what do I got? I got a rectangle. I'm sorry. Well, it is a rectangle, but a square, more specifically, plus half of this rectangle here. And so I just find those 2 areas of those 2 shapes and add them together. Well, there's 4 squares in the square, so that has an area of 4, or it's 2 by 2. And then this half of the 2 squares there is going to be 1, so this is going to be 5. And then G of 3 is the integral from 0 to 3 of f of t dt. So again, now we're just finding the area all the way out to here. We already know we have 5 units up to 2, so we'll exploit that. Let's go, I need this region right here. And so this is a triangle, half, base times height. The base is 1, 1, 2, 3, 4 for the height. So 1 times 4 is 4, divided by 2 is 2, plus the 5 from before, so that's going to be 7. And then we need G of 6, the definite integral from 0 to 6 of f of t dt. All right, so for this one, we're going to break this down into some different regions. Let's see, 3, 4, 5. So 6 is right over here. Whoops, when I'm drawing a 5. Let me count that again. 1, 2, 3, 4, 5, 6. Yeah, there's 6. So we know the area from 0 to 3 is the stuff that we had bounded here. We knew all this stuff was 7, or we know all this stuff was 7 because we had already calculated it. Now I just need to figure out the area of this stuff that's below, and since, whoops, I don't want, I just got rid of everything. Thanks. A little confused by the software at the moment, what it's doing to me. But now I just need to figure out this area down here and subtract it from the 7 that's there. Again, we're just breaking things up into regions that we could find. So if you look at it, we have half a square here and half a square here, so there's a whole square, and then 3 more squares, so there's 4 squares there, and 7 minus 4 is 3. All right, now on what interval is G decreasing? All right, let me move this up a little bit here and get rid of all this stuff. So where's G decreasing? Well, we have to remember that G decreases when G prime is, G is increasing when G prime is greater than 0. So what is G prime? Now remember, G of x is the definite integral from 0 to x of f of t dt. So what's G prime of x? Well, we just learned this. This is the fundamental theorem. This is taking the derivative with respect to x of the integral from 0 to x of f of t dt. You don't have to write it like that in the future, but just to link it back to the previous set of examples. The integral and the derivative cancel. I have it correctly set up. The lower limit of integration as a constant, and the upper as a variable. So those are going to cancel, and this is just going to be f of x. So I need to figure out now, to figure out where G is increasing, I need f of x, G prime, to be greater than 0. Where's that? Well, if we go back to the graph here, this graph is f, and where is this graph greater than 0? Above the t-axis? That's from 0 to 3. So G is increasing on the interval from 0 to 3 because G prime, which is equal to F, is greater than 0. Now, what's the next question? Where does G have a maximum value? Okay, so one thing that I would ask in class, if we were in class, is are we using, what method are we using for finding the maximum? And what kind of maximum are we looking for? Relative / local or absolute? Hopefully it's coming to mind that we're finding an absolute maximum. And we're finding an absolute maximum because they don't say absolute maximum or relative or local maximum. Remember, when there's no adjective describing the type of max or min, then we're finding absolute. So for absolute extrema, I need to either use the closed interval method or the first derivative test for absolute extrema. We do have a closed interval here. The graph is, it's closed interval from 0 to 7, okay? And so I'm going to find the maximum value on the closed interval from 0, the absolute maximum, using the closed interval method from 0 to 7, okay? All right, so how do I use the closed interval method? So the closed interval method, I need to figure out any critical numbers. So I need to figure out where G prime is equal to 0, okay? But G prime, remember, is F. So I need to figure out where F is equal to 0. And where does F equal 0? The only time F equals 0 on the graph is right here, and that's at 3, okay? That's when X is equal to 3. And when is G undefined? Or I'm sorry, G prime is never undefined. I mean, look at the graph. There are no points here where G prime does not exist between 0 and 7. Okay, so only critical number is G of 3. And so I'm looking for a max. How do I use the closed interval method again? I got to take the critical numbers and the endpoints. The endpoints are 0 and 7. Plug those into G and compare. So I need G of 0. Oh, we already did that. That was 0. I need G of 3. We already did that too. It's 7. Excuse me. And then I need G of 7. And I didn't do that one. I did G of 6, but I didn't do G of 7. G of 6 was 3. Obviously, G of 7 is going to be less than G of 3, but we'll calculate it anyways. G of 7, we have this one more unit of negative area here. This is base times height divided by 2 for that triangle. So this is 1 unit right here. So I need to, let's write this down a little bit. I'm going to use G of 6, which was 3, and subtract 1 from it because there's one more unit of area below the horizontal axis. So G of 7 is going to be 2. And so, therefore, the max is G of 3, which is 7. Notice I'm not saying the max is X equals 3. Remember, the max is the output. It's the Y value. So the max is G of 3, which is equal to 7. I'm going to leave it up to you to draw the sketch of the graph. You have plenty of points to plot, and you know when the graph is increasing and several things. So you go ahead and work out the graph of G. I'm actually going to stop this video here, and I've essentially covered all the important things about the fundamental theorem here with the examples and whatnot that you need to understand. But I'll make one more video to follow this one with some more examples for you to study. And I'm not sure I'll get that done today. I might get it done on another day. But you can at least, you have this one and you'll have another one with more examples coming later.